Why else would you want to measure phase if you are not NASA, JPL, people like that? Well, down here on Earth, sometimes you might just want to measure phase because you're characterizing something for which phase is important. For example, if you've got a clock source or an oscillator, maybe you've got a MEMS, a microelectrical mechanical system that you want to characterize, maybe it itself has some kind of phase properties that are worth looking at. Also for optical metrology, that's the kind of thing we were talking about there, where you're using lasers to measure distance, basically. And this isn't just satellites. You use optical metrology to, for 3D scanners or for on production lines for precision measurement of high precision parts and things like that. Quite often, though, you're going to want to go one step further than just measuring phase. You're going to want to lock phase, or at least control it in some way. You might want to do this if you have a coherent transponder. So this is a technique that's used in telecommunications in order to encode more information than you would be able to with other modulation methods by locking the phase of typically a receive and a transmit beam, or at least a receiver and a transmitter. You might also want to lock the phase of two things for coherent beam combination. Again, this is a laser thing, this is an optics thing, but this is Optica, so forgive me if I bang on about it a bit. Coherent beam combination can be used for things like defense applications, for weaponry, basically, for combining power at a target. It can also be used for powering drones. You can combine lasers onto like a PV, a photovoltaic panel, in order to power the drones without having any cables and without them having a battery that needs to last forever. The image on the screen there is of a project called Breakthrough Starshot, which is a little bit of a grandiose name, I suppose. But the concept behind Breakthrough Starshot is to deploy a swarm of potentially up to 1,000 or more than 1,000 tiny little, like gram scale, like 1 gram kind of size satellites, or at least spacecraft. And you tether those gram-sized spacecraft behind a huge reflective sail. This is deployed up in space, and then you shine a laser on the sail, and the photon pressure from the laser is designed to accelerate the spacecraft up to a significant fraction of the speed of light, and hopefully point it in the direction of something interesting, like one of our celestial neighbors. And ideally within 20 or 30 years of travel at maybe 80% of the speed of light, we would be able to get a satellite out to other star systems. When they're there, ideally they can take some photographs, send us back the images that they've received, or that they've taken rather, and those images coming back might take like 4 years to arrive, but nevertheless, the idea here is to get satellites out to other worlds, which seems pretty exciting to me. In order to do that, though, in order to accelerate even these tiny spacecraft up to a significant fraction of the speed of light, we'll take something like 100 gigawatts of power, of laser power, focused onto these sails. Given that a decent-sized nuclear power plant might churn out about 1 gigawatt, this is a lot of power. So in order to do that, you're not going to use one big laser, you're going to use lots of smaller lasers, but you need to make sure that those beams combine constructively in the far field at the sail so that you actually get the photon pressure that you're looking for.